Okay.
Or also, you can start with R is equal to R hat, and do the second derivative there also. All right, so centripetal acceleration, this is the acceleration towards the center, is equal to negative v squared over r hat. And that's right, I'm about to define r hat. R hat is a unit vector, that's why they have the hat. So it's a unit vector pointing away from the center. Now, when we deal with I hat, j hat, k hat, we define the I hat direction, we define the j hat direction, k hat comes naturally out of that in a right-handed coordinate system. Unit vector, the r hat, the radial unit vector. It's called the radial unit vector. Our decision here is where's the center? What's our reference? So if something is traveling in a circle, then the radius of curvature, the center of that radius of curvature would be the center that we're talking about here. The negative means opposite of away. Since r hat is away from the center, negative r hat would be toward the center. Questions before we actually go through the process? Start out with the table problem. I got a table, there's a hole in the middle, I got a mass that is swinging around. So let's make this a 2 kilogram mass. Make this a 4 kilogram mass. The table frictionless. So this is a side view. Overhead view. This mass is swinging around. The 2 kilogram mass. It's swinging around in a circle, and let's say it takes, let's say I need to give some information here. So we'll have a radius of 3 meters, make it really big. And actually, I don't need to tell you the time. What we're gonna do is, how fast does this need to swing, or what is the time it takes for this to go around, do them both, in order for the 4 kilogram mass to be in equilibrium. Static equilibrium, more specifically. So speed of the 2 kilogram mass so that the 4 kilogram mass is in static equilibrium. All right, for any questions on visualizing what's happening in the problem?
Is this like on top of a table?
Yeah, on top of a table, a frictionless table.
Is it? It's not like hanging over the side. It's just.
No, it's doing something like that, except not falling off. It's that type thing,
So
without
then-
the friction.
There's a hole.
Yeah, hole in the middle of the table.
And is it, so then how does how does the 2 kilogram mass spin when there's the hole?
Ask that again?
How does the 2 kilogram mass spin when there's like the hole with the 4 kilogram mass?
And how did it start spinning, or?
How is it spinning?
It came into existence already spinning. How it got to that position is irrelevant. All we know is that it's spinning on a frictionless table. No air resistance. As I've seen it credited to more than one physicist, but we'll credit Einstein this time. As Einstein once said, the future is more certain than the past. Because from this, we can predict what's going to happen in the future, but how it got to here, don't know. We're going to go through the exact same process that we went through on the non-spinning problems. Any of you missing?
You can turn it off.
Yeah, Harnett County, where is that? Okay.
Probably at sea
Probably what?
in North Carolina.
I would guess North Carolina. But it could be, we're not that far from Virginia. All right, so the force diagram. I have two masses that I care about, so now since the top mass, the 2 kilogram mass is spinning in a circle, there are many places I could take a look at it, but I'm just gonna pretend it's at that position at the moment. We're gonna basically take it as it's spinning, we're gonna take a snapshot, it's right there. And I wanna know the forces acting on it. And then we've got the rope. I'm not gonna bother writing the table into this problem. There's your 4 kilogram, your 2 kilogram. All right, what are the forces? Need that checklist?
Tension.
Okay. So I have attention here, attention here, attention here, attention here. Sorry if I spoiled that for you.
Gravity. Or wait.
Acting on,
Acting on, we're not on both the masses.
okay, assume it's an ideal rope. So I have W2, W4. If we're doing a complete force diagram, I'd have forces acting up on the ground. All right, that's it. It's supposed to be a check mark and not the number 2. Next. Oh, don't make Dominic do this.
Friction, right?
Frictional stable. That won't make it that hard.
Just normal force.
Acting which way? On what?
It's down on 2, right?
Is normal force is pushing 2 onto the table?
Yeah. No.
Normal force keeps something from going, it does the opposite of pushing onto a table.
I'll say so. Up.
Oh, yeah. All right, we've got a normal force there.
And down on 4.
What is 4 touching? Normal force requires contact. Yeah, there's no normal force acting on 4. It's not really pressed against anything. It is touching the rope for those who want to take that part. However, since we don't know how the rope is attached to 4, we're calling it tension. So we don't have to worry about whether it's being held on by friction or by normal force or whatever. So that's what tension is. So that's it. It's only that one. Normal force done. Well, actually, there is another normal force. It's irrelevant to solving the problem, but there's another normal force given the objects I have here. Yes. There's a reason the rope is bent, so there's a normal force somewhere in that direction. I'll call it Y sub R. And also acting on the table. And no friction, no other. All right, that's it. What I really care about is this and this. If the rope were not ideal, then I would worry about this also. Acceleration. what will be the acceleration of, or in which direction will the 4 kilogram mass accelerate? Why?
Because it's not touching the ground, and assuming it's staying in equilibrium, it's not going to be going down.
Okay, so why up?
I mean, I guess it's not moving either. I guess there is no acceleration, or it's just staying still, right?
Yeah, well, not only is it staying still, but it is, if it's in equilibrium, immediately acceleration is 0. So what's the direction of acceleration?
Is it not?
Whatever we want it to be. Or more specifically, making which direction we want positive is whatever we really want it to be. Over here, what is the direction of the acceleration of the 2 kilogram mass?
All of them? All the directions? 'Cause it's going in a circle.
At that moment, at this moment, we take the snapshot, what is the direction of acceleration?
Towards the center.
Yes, which is in which direction at this moment?
To the left. To the left.
Yes. So this has acceleration pointing towards the center. Matter of fact, I'll put a little subscript C there because it's really centripetal acceleration. All right, so decomposition, do we need to break anything up? This properly. All right, so equations of motion. Oh, coordinate axes, I skipped that. So for the coordinate system here, we already talked about acceleration is 0. It's a one-dimensional, we have only one dimension of forces, so up is positive or down is positive. Doesn't matter, pick one.
Up.
All right. Over here, let's set up our coordinate system here. What should be the I-hat direction?
Left.
I heard left. So we'll make that I-hat. And J-hat? We'll make down, okay. If you don't like it being down, you should have split it up soon. Ideally, those would actually be drawn at the same length. Equations of motion. When we're plugging into equations of motion, what's our template? What's the form that we do an equation of motion?
Force equals mass times acceleration.
That's the one. How many equations of motion will we have?
3.
Right? All right. So we'll have our I-hat equation, our J-hat equation, and then our, I'll just say mass 4 equation. Somebody give me one of the equations. I think at this point, there's only one voice I haven't heard.
I messed it up bad last time. I don't even try.
That's okay.
I don't even want to attempt it.
Okay.
I mean, I hope it will. Yeah, ask it.
All right, I'll call it this something else later. Or actually, I've now heard your voice in this class, so now I've heard everyone's voice. Dominic, give me one of them.
Going for I-hat.
You okay?
There's nothing on the negative side for, right? I'll do J-hat. I'll do J-hat instead.
Okay.
It would be weight.
W2.
Yeah. I don't do. There's no. It's not an angle, so there's no cosine or sine in it, correct?
Correct. That would have shown up probably at that point.
So weight minus the normal force is equal to something.
You are correct. Let's see if we can narrow that down.
M times A, right?
Say it again?
M times A? Or M A, right?
So M2 times
Two
A.
times A, right?
What is the acceleration? This is this direction. What is the acceleration this way?
Oh, 0.
Yeah, 2, 0. All right, one down.
FT, or I hat is FT is equal to M2A.
And I'll put a little cease there because it is centripetal acceleration. And let's see, one more equation to go. Oh, don't make Dominic do this. All right, I'm gonna let them make you do it. Dominic.
Weight 4 minus FT, because up is positive for this one, correct?
That's what I was told.
Yeah. So weight 4 minus FT, or is it am I saying it backwards?
Yeah.
FT minus
If
weight
up is positive.
FT minus weight 4, yeah,
Okay.
is equal to M4 times 0.
All right. It's in equilibrium. So we've already established the acceleration is 0. All right, so we have our base equations right there. Now it's time for a little substitution. For of our equations there, for what do we have? An independent equation. Something that does not rely upon this problem. What is the formula for weight?
There's a 9.78 in
MG.
Thank you. What is that 9.798 you were saying? What is that?
it. The acceleration.
Okay, skip the whole thing. Weight's a force, so it can't be 9.798 meters per second squared. What is the acceleration?
Due to gravity
Okay, acceleration due to gravity,
is G.
little g. Where is that the acceleration due to gravity?
Out in the middle of the road, right up there.
Yep, there we go. Or I would have accepted Winston-Salem as well, but yes, definitely. All right, so this equation right here now becomes M2G equals Y. Go ahead and throw that to the other side. And this equation right here is we have tension is equal to M4G. All right, what other formula do we have that's independent of this problem? It's not tension, it's not normal force. And it relates to the topic we're talking about. Natalie?
Centripetal acceleration.
Yes. Now the negative r hat is the direction, but we already know the direction is towards the center, which we defined as a positive direction here. So this first equation becomes tension is equal to m2 v squared over r. So my three equations at this point, we have y is equal to m2g. Tension equals m4g, and tension equals m2 v squared over r. Just rewriting the three formulas we have right there. I'm solving for v. I don't know the tension, I don't know the normal force. Well, I can find the normal force easily enough once we identify what planet this is on. What planet do you want to put it on?
Earth
Earth
2.
8.
I heard 2 first. So since we're on Earth 2, so E2, G is 10 meters per second squared. So this is equal to 20 meters. That is equal to 40. Or I'll hold off on that one. So we have M4G equals M2 V squared over R. Solving for V, I have V is equal to M4GR over M2 square root. I know M4, I know M2, I know little g, I know R. Pretty sure that was given. Oh, it's on the other page. So it's now plug and chug. Square root of 4 times 10 times 3 divided by 2. 7 point something.
Why is the acceleration V2 divided by R and not negative?
The negative is, that negative r hat tells me the direction means towards the center. When the system was set up, we set up the positive direction to be towards the center. So that's why we don't need to include the negative, because we've already taken that into account. If you do put the negative in there accidentally, you'll end up with a negative under the radical, which means that either the problem is impossible or there's a mistake somewhere.
7.7457 459.
7.459
7459.
units?
Newtons.
Nope. What do we find?
Radian.
Oh. Meters a second.
Say it again.
Meters a second. Meters?
Meters a second, I guess, traditionally meters per second.
Oh.
All right, so we have how fast it's going. How long does it take for this object to go around the